Yeah, my name's Justin. I'm a pure functional programming fanatic. I work at YoppWorks. If you don't know YoppWorks, we provide training consulting in Scala, domain-driven design, reactive architecture. So you should check out our booth because we have a really funny t-shirt as well. So yesterday we saw a couple of good talks about using pure functional programming to solve real problems like at Netflix and Comcast. And those guys were using CATS, HTTP4S, FS2. These are libraries that are built on principles of pure functional programming, and also they use parts of category theory. So that's great for me because my talk is my talk's aimed at people who are kind of getting interested in pure functional programming, and then we'll work up to Comonads, which is kind of a more unusual topic. So what is pure functional programming? It's programming with functions that have various properties. So we begin with a function that maps a type A to a type B. One of the properties of the function is that it's total. So this means that for all, say if A was an integer, for every value of A, you're going to get a value back from B. You're not going to get null, or you're not going to get an empty or some kind of error. You always get an answer. The other property is deterministic. Which means every number we put in there, we're going to get the same answer back. Pure functions have no side effects. So we're not going to be writing to a database. We're not going to be mutating any data or doing anything useful, basically. So advantages of pure functions, if we program this way, we get programs that are inherently easy to test. We get equational reasoning, which means we can use algebra to manipulate our programs and see how they work, see if they're doing what we want them to do. And we can also compose them. And also type functional programming gives you this advantage that you can, if two things line up, the types match, you can usually compose them and do something. So pure functions need help to solve real-world problems. So one thing is side effects. So a lot of useful programs are going to write to the database, they're going to make network calls and so on. So we use the I/O monad, and what that does is it kind of wraps side effects up so they can be run later. We can still use our pure functional code with the side effects. Another thing is partiality, which is the opposite of being a total function. So a partial function doesn't have an answer for everything. So an example might be if you look up some money in a database and they're not there, you'll get a none instead of the person you wanted. Another thing is exceptions, so monad error helps with that. Non-determinism, which means just handling lists. And mutable state, we have the state monad that can help with that one. So all of these things are included in the CATS functional programming library. And CATS is really accessible, it has a great user community, so you can always get help. And it provides all of the things that make pure functional programming usable in real code. Another thing is a lot of these concepts come from category theory, which is a branch of mathematics that describes mapping objects. And there's this really great book you can read for free online, and also a video series that introduces category theory. And you don't really need it to use this stuff, but it's kind of fun and interesting, and it's quite accessible. So CATS comes with this large menagerie of type classes that are basically things to help you take your pure code and use it for useful programs. So last year I watched a talk by Rob Norris, and he said, find Functor, find Monad, and see what's nearby. So he was talking about this. So this talk is pretty much, I did exactly what he said. So here's Monad. And there's Functor. And you can see that Monad is related to Functor. It goes up like this subtyping relationship. And just adjacent to Monad is Comonad, which is also related to Functor. So you can see how these categories are all kind of related. So type classes are implemented like this. They're kind of like interfaces. A type class provides a function. So if you want to be a thing that implements the show type class, then you have to implement this show function, which takes some type A and turns it into a string. So here's an example of that. We just have our own data type, the person. And by creating an implementation for the type class, we're basically telling it how to do the show. And then in this example, you can see that when we print it, we get this more interesting output. So Functor is actually from category theory. And what Functor is doing is, for all of these things to understand what they do, we just need to look at the type signature. So first of all, you can see that the Functor is implemented for some type F, and then we have this underscore, which means that it's going to be further specialized by another parameter. So F might be, say, a list or a future. And then when we implement the map, when we call the map, these other types come into play, the A and the B. So if you remember from the start of the talk, I had my A to B function. That's one of the parameters to Functor. So what Functor takes as a parameter is that and this impure value. So we have this f of A, which means it's a pure value, but it's been somehow put into the impure world. So it might be an asynchronous operation or a list or one of the other things we talked about before. So then we're going to apply this function. So you can see that what a functor does is it can take the pure value out of the effect and then run your pure code on it. And that pure code is code that you can test and reason about and all those good things. And then it's going to wrap it back up in a new f with the result type wrapped up. So here's an example of that. And if a lot of you are Scala programmers, you're probably familiar with mapping, just mapping a list. But this is a high-level view of it. You're not just mapping a list, you're transforming a list using a pure function. So another common type class is Monad, which is the subject of our funny t-shirt. So Monad has two functions, the pure and the flat map. What pure does is let us take a pure value of type A and put it into our effect type. So you can see this simple example, which is putting it in a list. And then Monad also has flat map, which takes functions that have this signature. So you have a pure value, in this case an integer, and it's going to map it into a list. And these functions show up all the time in real code. So like doing a database lookup, for example, would take a user ID and might return a task of user. And then we have another function here, which is the same as signature. And what we want to do is to be able to compose these functions. So in the last line of this one, you can see that when I call this one, I'm taking this pure value and putting it into the list effect. Then I flat map it, and what I get out is this flattened list at the end. So if we didn't have flat map, if we only had map, then what we would get instead is this nested list. And if you think about if you were doing a database query instead of a simple list operation, that's not what you want, because it's harder to get inside. You have to kind of go 2 layers in to get the thing that you wanted. So Yeah, so flat map is a map followed by flatten, hence the name. And you can see from this type signature that it's taking your result list and squashing it down to a list. And more abstractly, it will take f of f of a and map it into an f of a. Okay, so now we get to Cothings. So Cothings is, not many people talk about Comonads or Cothings in general in Scala books, but this book does have a chapter on Cothings, and it's also a good book because it teaches you how to build practical functional programs, and it covers Scala Z, which is very similar to cats, but it's pretty much the same. Okay, so here's the Comonad. Comonad is, it has kind of the same functions as the monad. And that's why it's called a comonad, because it's the co-thing to a monad. And the difference is that all the operations it has have that types going in a different direction. So the pure function in monad is able to take a pure value and put it into the effectful world. But the dual of that is extract. And the type signature of extract is to take something that's already in the impure world and pull it out, giving you a pure value. So the interesting thing about that is you can't implement it for every kind of object, because the type signature is telling you what you're going to get. If you have an effectful A, we're going to give you an A. So that means that if you have something like a list or an option, you can't implement the extract function because there's nothing to get out of it. So that means there's no valid implementation. And because it's a pure function and strictly typed, we can't just throw an error or return none. So we can't do extract for list, so we just don't implement it. But we can use the non-empty list, which is something you get with the cats library. You can tell from the name that non-empty list is a list of things that can't be empty. So you can't make a non-empty list with nothing in it, and you can't take everything out of a non-empty list. It just, from the types, it just doesn't let you do it. So the extract function for non-empty list could give you any member of the list, but just to be deterministic, it's implemented to always give you the head of the list. So in this case, you just get the one. So this slide is about unflatten. So unflatten is not really, or coflatten is not really part of the Comonad, but there is an unflattening operation in the Comonad coflat map. So this is just illustrative to show you how you would implement it. So when you flatten something, like before we flattened a list of lists into a list, coflatten is the opposite. What we have is a flat list, and we want to unflatten it into a nested list. So where does that magic extra stuff come from? What you get is this is the cats implementation of coflatten. And what you get out is you get the original list, and then you get the tail of that, and the tail of that, and so on until you've only got one element left. So it's giving you a nested non-empty list. So that's where the magic data comes from. And when you implement coflatten for your own custom data types, you can come up with different ways to implement this idea of expanding out into a new level of effects. So here's an example of using coflat map. So remember that flat map was a flattening operation followed by a map. What coflat map does is first it does that unflattening operation that I talked about, and then it maps a function which collapses that down into a list again. So in this case, you can see we started off with a list of these numbers, and then the function we passed to coflat map has the signature of being an effectful A being mapped down to a pure value. So in this case, we're taking a list and it's going to be each one of these lists that we got from our coflatten. And then we just get the sum of that list. So you can see that the type signature is going from effectful to pure. So essentially we have this unflattening, and then the flattening is done by the function that we passed in. So all the category theory things have laws, and one of the laws of Comonads says that if I call extract, if I pass extract as a function to coflatmap on a thing, then I should get the identical thing back. So you can see that at work here. And that kind of illustrates why we did this kind of weird thing giving you the tails of the lists, because that makes the laws pass. It makes this law pass. So conceptually what we're doing is we're unflattening a list to the list and all of its tails, and then we're getting the head of all those lists, which is the original list. Okay, so now we come to like a practical example of how you would use a comonad in the wild. So I made up this data type, and this data type represents a two-dimensional array, and we're looking at a particular row and column of it. So we store this thing called a focus, and it's just a tuple. So this represents a row and a column of the array. And then we store this grid, which is a 2D vector of, we can parameterize this later, so it can be integers or any type you want. So yeah, so to use the Comonad, we need to implement the Comonad instance for this new data type. So we have to think about how we would implement extract and coflatmap. So extract is easy. We're just looking at a 2D grid. The focus point is the point we're looking at. So we can just say extract that value from the array, and that's the extract function. So coflatten is more interesting. So what you're looking at here is a focus grid of focus grids, and the way that it blows out is we're going to look at every point. So the kind of outer focus grid is just focused at the origin, so that's this 0, 0. And then each of these focus grids is just the same array as in the original, but we're looking at all the coordinates. So you can see this one is looking at 0, 0. And then you have 0, 1, 0, 2. So that's the top row of the grid. So essentially, the unflatten is letting us look at the whole grid, one thing at a time. So what use is that? Well, it gives us this, it means the type signature that we're going to pass to coflatmap is going to take a focus grid and return a pure value. So that means that we can build functionality that requires to looking at something from a broader context and then mapping it down to a more narrow context again. So in this example, I make a box filter. So a box filter is kind of an image processing technique where you just take a grid of all the pixels around a pixel in an image, take the average of those, and that's the new value for that pixel. And if you do that to the whole image, then you can filter the image out. So there's the original, not my artwork. And then we're going to blur it with the parameters 5. So this is basically a grid of 5 pixels. And that's 15, so it's more blurred. But you can see that we haven't written much code here. We've just got this one function, and then we've got the actual algorithm of mapping over the grid is encoded in the Comonad instance that we made. You can also compose these things together. So another simple transformation is to do mirroring of an image, which just means if I'm looking at a particular pixel, I can just look at the pixel mirrored down the middle, and that's the new value of my pixel. So you do that for the whole image, and it will mirror it horizontally. So in this example, we've first filtered and then mirrored horizontally just by composing these functions in these coflat maps in a sequence. So here's a more involved example. This is a bit more complicated, but it gives you an idea of, you can use all of the things in the cats library now. We've made this part of the, we've made this pure functional thing. Now we can compose it using all of the things that we've got available in cats. So in this example, what it's doing is two operations at once, mirroring vertically and mirroring horizontally. And then it's taking the product of those, which is going to give us a new image, which has 2 pixels for every pixel. And then finally, it blends them using the map, which just averages them out. So again, this is all from composition, composing things we already did. And then you can get this weird image. So another example, in previous talk today, we saw Conway's game of life implemented in functional reactive style. This is pure functional style, solving the same problem. And the only change we need to make is to implement this function, which takes a focus grid and returns a single integer. And then we can represent the Conway game of life grid with 0 for dead cells and 1 for living cells. And then it's a pretty readable mapping of the Conway game of life rules into this function that we're going to pass into coflat map. And then down here at the bottom, you can see how we call that. So we have an initial grid, and then we coflat map it with this function. And then I'm mapping it to a function called prettify, which just takes those numbers and turns them into more interesting characters to display. So luckily, cats library can be is ported to Scala.js, so you can use it in the browser. So you can use Scala Fiddle. So I just pasted my code in here and hooked up some graphics. And you can see the game of life animated in the browser. Ta-da. Okay, that's my talk. Thanks. So I think I do have some time for questions, if anyone has one.
When you're calling coflat in there, you're creating a bunch of redundant data. Are there implications for efficiency with that?
Yeah, that's a good question. If you look at that data structure in the image, in the slide, there is some duplication, but the actual array data itself is not duplicated. It's going to be a reference. So there's not a huge amount of duplication. But that said, I'm not suggesting that you use this kind of structure to do lots of high detail image processing, but certainly for it certainly works pretty fast and uses not that much memory in this kind of use case.
Okay, great. Thanks, Justin.